So today we'll be seeing about parse tree and ambiguous grammar. Today we'll be discussing about what is derivation tree and how a derivation tree can be formed using leftmost derivation and rightmost derivation. We'll also see about what is an ambiguous grammar is. So derivation tree, a context-free grammar can be represented using trees. So such trees are called derivation tree. So what is a derivation tree, which is otherwise called parse tree, which is for a context-free grammar, it should satisfy the following conditions. So the first condition is a leaf node should be a terminal, a root node must be your starting symbol, the interior nodes must be non-terminal symbols. So if you are having any interior nodes, that is if you have a path from root node to some leaf node, means suppose its descendants are x1, x2, x3, then there must be a production rule such that A implies x1, x2 up to xn. And if a leaf node exists, then that leaf node should belong to the terminal, and it should be a parent of some non-terminal variable. Okay, so this is the properties that it should satisfy a derivation tree. Now let us see an example. So I have given a grammar E is equal to E plus E star E, and E implies ID. So how a derivation tree can be derived for the given input string ID plus ID star ID. So we can derive it in this form. So I will take first the production rule, E is equal to E plus E. So for the first E I will substitute E plus, for the last E I am substituting E star E, then I am substituting ID for each E. So this is how the derivation tree will be done with the form. So what I did, E plus E, so E will be your starting symbol, so E plus E, then I have derived E star E, then all the E's are been replaced with ID. So this is how a parse tree will be constructed for them. So here the derivation is neither LMD nor RMD. That means I have not used a leftmost derivation or rightmost derivation. It's a mixed derivation I have done. Before that I have created a parse tree. So we have two types of parse tree. One is LMD tree and RMD tree. So if you are using leftmost derivation, the tree constructed from the leftmost derivation will be a LMD tree. And if you are using rightmost derivation, then it will be called as RMD tree. So these are the two types of tree we have for parse tree. Okay. And what is a subtree is? Subtree is of a derivation tree is nothing but a particular vertex of a tree together with all its descents and edges for connecting them and their labels. So here the derivation tree, except the label of the root, it can be a search symbol, and all other variables root we can call it as a subtrees with that particular label. So if you have a descendant for the root node, then that root node can be named with the non-terminal label. So that is considered as a subtree. Now you see you are given a CFG grammar with the production rules, and we have to show that the given string is accepted by the CFG or not. So let us start from our instruction. So I have given all the production rules, so you can have numbers for that. So we'll put numbers to this 4, 5. Okay, so we'll start first here. So S tends to AS. So S is the starting symbol, so we use S for this. Now what is the string I need is A. Again, secondly I need again AB or something combination. So to have, you can see S has A, but A does not have. So let me take this A can be replaced with SBA. That is rule number 3. So you can write it as AS BA S. Now instead of this S, I can substitute rule number 2. So you will have AAB AS. Now you can see I have derived 3 symbols from the input string. Now the remaining is BA. So instead of A, I can substitute BA using rule number 5. So you will have AA, BA, then S. Finally, you can see I need only one A. It is BA. I left B over here. So it is BAS. Now finally for S, I can substitute rule number 2. So you will have AA, BB, AA. Let us draw the state variation diagram. So the string is accepted. So we will draw the state parse tree for this. So starting from S, you have derived A, capital A, then S, and for A we have substituted SBS. So S, B, again A. Now for this S I have already substituted A, and for this A I have substituted BA, and for the finally the S I have substituted A over here. So I'll draw like this, S A. So when you travel only through the leaf node, when you see only the leaf node, you can see it has the string constructed. So the string will be, you can see A, B, B, A. So it is A, B, B, A. So this is how we will check our string is accepted by CFG using parse tree. So now we are going to check the string, whether string is accepted by the CFG using parse tree. So we'll see how it is done. So first thing is, you'll write a rule here. So to have BB, AA, to be accepted, so I'm going to use first S implies XX. So we'll draw the parse tree for that, X. Now for the first X, you can substitute, we need B, so we'll use BX. So now I will use BX. So that means for the first X, I am substituting BXX. Okay. Now I need one more time, it needs a BX. So again, this X can be replaced by BBXX. So I will replace that with B and X. Then I need A. So for X, let me substitute A alone here. So BBAX. So you will have A over here. Now for this X, again you need, how many A's is left over? I need 3 A's more. So I will replace this X with 3X. So I will be replacing with BBAXXX. So you will have X and X, right? So for the first X, I will substitute A, and for the second X, I will substitute A. So what happens is it will become BBAAXX. Then finally you will have BBAAX. So I will draw A and A. And for the final X, you can see it needs AB. So what I will do is I will substitute XB over here. Okay, so we will substitute XB. So now it will be BBAAXB. So you will have an X and you will have a B. Then for the finally the X, you will substitute A. So you will have A B. So finally for this you will have A. So you can see double B, triple A and B. So the string is accepted by the CFG. We'll see the next example. Now this example, you are asked to find LMD, RMD and you need a derivation tree. So let us start with the LMD first. So I will use S tends to 0B first. Now instead of B, I will substitute 0BB. So you will have 0BB. Again, instead of B, I can substitute 1S. So I can substitute 1 as well as 1S. So let me clear this first B first alone. So I will substitute 1B. Okay. Then for this B, I can substitute 1S. So 11S. Okay, I can substitute 1S. Now for S, I can substitute 0B. You can see the rule. Okay, 0B. Again, for this B, I need 1. So you can see I can substitute either 1S. Okay, so I will substitute 1S because I need 1 over here. So 1S. Now instead of S, I need again 0 over here. So I can substitute 0B again. So you will have 0B. And finally, instead of B, we can substitute 1 over here. So 0. So this is the leftmost derivation. You can see I am traveling from leftmost to the rightmost. You can see in 2 B's I am taking only the left B. Now the rightmost derivation, So from the right side you have to substitute the derivation. So we'll take same one. So I'll take 0b first. So now instead of b I will substitute 0b. Now instead of this b I will substitute, I need, what is the last term I need is it's going to be 01s. So b does not have ending with 1, so you'll use 1s. So we'll substitute 00b 1s. Now instead of 1 I can again substitute 0b. So because we're going to substitute this three terms, okay, 0 1 0. So you will have 00b 10b. Now instead of this b I can substitute 1. So 00b 101. Now instead of this b, what is remaining middle term I need is double 1. Okay, so what you will do is it's 0. Wait. Instead of this again, let me correct this one, bs. So it's 1 not bs. Instead of b I'll use s again. Okay, so 1s. Now instead of this s I may substitute again 00b 1010b. Okay, so I am getting the last term. So again I will substitute 1 over here. So you will have 00b 10101. Now finally this b can be replaced with 1. So you will have 00110101. So it is also accepted in using rightmost derivation. So to draw the derivation tree, you can use a LMD or RMD. So I am going to use a LMD over here for my derivation, that is my parse tree. Okay, so for parse tree I am going to use a LMD. So we start with S. So S is given with 0 and B, and for B I have substituted 0 BB. So I will use 0 B, then B. So for this b I have substituted 1, so I have 1, and for the next b I have substituted 1s, so it is 1s, and for this s I have again substituted 0 b. Okay, and for this b again I have substituted 1s, and finally for this 1 I have substituted 0 b. Then finally for this b I have substituted 1. So now see the leaf node alone, whether you get the string. So it's going to be 0 0 1 1 0 1 0 1. So this is the parse tree for using the LMD for the given problem. Same problem for the given grammar, you have to draw LMD, RMD and the parse tree. So let us try for LMD first. So I'm going to use LMD for the given string. So the given string is triple A, double B, A, triple B, A. Okay, we'll start with the substitution. So S tends to AB first because it starts with A. So now for B, I will substitute again AB, A, B, again B. So we need 3 A's. So let me consecutively substitute A, B, B, B. Now for this B, I can substitute B alone. So A, B, then B and B. Now for this B also I can substitute again B. So let me substitute A, B, B. Then you will have B. Now for this B I can substitute the last production A, B, B. So you will substitute that. So it will be A, B, B. Okay. So what I need is next again I need two B's. So what I will do is first I will replace A, B, B, A as B for this B. Now this B will replace it. I need another two more B's. I can replace it with BS. Okay, so I will replace it with A, B, B. So I will replace it with BS again here. So A, B, B, A, B, BS. So why did I substitute with BSS? Because after B again I need A. So we'll substitute, instead of S I will substitute BA. So you will substitute A, B, A. Okay, and you will have triple B, A. So finally A can be substituted with A alone. So you will have A, B, A, B, 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 A. So my string is accepted using LMD derivation. Now we'll check with the RMD, so rightmost derivation. So we'll check with how rightmost derivation works. So we'll start with S tends to AB. Okay. Now this B has to be replaced, so I will replace with ABB again. So AA, BB. Now this B has to be replaced, so we are taking the rightmost, so we'll have BS. Okay, ABB, BS. Okay, so the last 3B has to be generated. So we'll take again S over here, we'll take BA here. So we'll replace AA, B, 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 A. Okay, so the final A can be replaced with A over here. So the final end of the string can be generated. So I will have 2B and A. Now coming to the middle one, now I need the in between string. So I can replace this with a double B, then B, B, A. Now the rightmost B should be replaced. So the rightmost B, I will replace it with B itself. So A, B, 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 A. Now this I have to replace with A. Okay, so I will replace with B only. So I have 3 A's already. I need only double B and A. So we will replace with BS. So you will have A, BS, then B, 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 A. Now for this S, I need only one BA. Okay, so we can substitute A, B, B, capital A, then B, 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 A. Now this A can be replaced with A. So A, B, B, A, B, 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 A. So we have derived the rightmost derivation for the given string. It seems that the string is accepted by the grammar. So with the previous LMD and RMD derivations, so we have constructed the parse tree based on how it has been derived. So this is the parse tree for the given problem. Now we will see an example. So what is the example given here is you have to construct the context-free grammar for the given regular expression. Okay, so the regular expression here is A plus B the star. That means it can have either, so the language generated will be either it will be epsilon, it can be A, or it can be B, or it can be AB. Okay, so this is the language that is generated for the program. So how to form the context-free grammar? So we'll have S tends to epsilon, so it can be in empty, it can be A or B. So we'll write A or B. Okay, so then we'll have an epsilon part over here. So it can start with multiple A's or multiple B's. Okay, so the thing is over here is I can have multiple A's and multiple B's. So it will be like AAB or BAA or BBAA. So or AABB, so anything it can generate. So I have to consider this case. So multiple A, so we'll have AS, so S can replace B or an A, or BS, it can have B and A. So this is the grammar given for the tree. Now we'll take a string and we'll try to form a parse tree for that. So that you have to draw a parse tree for the given string. First you will write the grammar first, CFG grammar. Okay, we'll write the CFG grammar over here. Okay, I'm making it right. So CFG is going to be, your symbol is going to be S, only one non-terminal, and terminal symbols are A and B. Okay, and start symbol is S. My production rule is S tends to epsilon, or A or B or AS or BS. So this is the context-free grammar. So now we need to accept for triple A, whether triple A will be accepted by this grammar or not. So we'll start with AS first. So instead of S, again I will substitute AS. So AAS. Again, instead of S, I can substitute A here. So string is accepted. So draw the parse tree for that. So you can draw parse tree like AS. Again, I can have A and S. Then finally I can have A. So this is another type of problem that you have to construct and construct free grammar from the regular expression, and make sure that the string is accepted by the context free grammar, and we have drawn the parse tree. Let us have a similar example again. So the regular language R is going to be 0 star 1 0 plus 1 star. So you can have multiple zeros or without anything before 1. After 1 you can have multiple zeros and 1. So your language will be like, it can't be empty because 1 must exist. So you'll have 1. You can have 0 1 0 1 0 0 0 1. Okay, and the next part we can have this one. So 0 1 0 1, or you can have 1 0 1, or 1 1 1 1 1, or 1 0 0, or you can have 0 0 1 0 0 1. It goes on. So we should make sure that a grammar has to be generated. So first thing is, we know that it is not having epsilon. So let me take one part. So we have this one and this one. We will take it as a separate equation. So one is must. So s tends to 1. We'll have first part as a and second part as b. Now what is a tends to? So a can be only of multiple zeros. So you will have 0a. So a can be replaced, and a can be epsilon. So after multiple zeros, a can be made an epsilon. Now b can have either 0 or 1. So what you will do over here is, so b is equal to, it can be 0b or 1b, or it can be epsilon. So let us check the given string 0 0 1 and 0 1 can be accepted by the grammar or not. So we will start with a1b. Okay, so now I can use leftmost derivation. So a has to be replaced, so I will replace with a01b. Now again I can substitute a001b. So I have substituted here. Now this a can be made epsilon, so I will make it as 001b. Now b can be replaced with what I need is 01, so I will take it as 0010b. Again b can be substituted as 00101b. Finally this b can be given as 00101 epsilon. So finally you will get 00101. So string is accepted. Now with this derivation we will draw a parse tree for the given string. So we will start with s. So you have a 1. It is now 1 over here. So 1 b. Now a is substituted as 0a, then finally 0a, then finally you have epsilon. Now this b is substituted as, first one is 0b, then it is substituted as 1b, then finally this is epsilon. So you will see the string, it's 0 0 1 0 1. So it is accepted. So this is the parse tree for the given regular expression. So we will have a similar expression. So here my regular expression is r is equal to a plus b star. That means a and b can be multiple, but you must compulsorily have a then followed by a or b. So the language generated is, you should have compulsorily a, then in before you can have any a or b, and after a double a you can have a or a, then you can have multiple a and multiple b's after that. So it goes on like this. So now I need to frame the context-free grammar over here. So s tends to, so we'll take two parts. So this is one part and this is one part. So let me have it as both are same expression. So I'll have a alone. So a. So what will be a is, you can have a or b. So you will take it as in the form a for a. If you want b alone, you will have to write ba, and it can be of empty. So my context-free grammar G is going to be my state s comma a. My non-terminals are a and b. My start symbol is s, and my production is s tends to a, comma a tends to a, ba, or epsilon. Now we will check the given string is accepted. So what is the given string is triple AB. So let me start with a. So we will start leftmost derivation, so I'm going to use leftmost derivation, so I will substitute AA double A. Now this A can become epsilon, so you will have A capital A. Now instead of this A, I can substitute BA. Okay, so I can substitute BA, so I will substitute A, B capital A. Now this A can be an epsilon, so it will be triple A B. So this is the derivation for making the string accepted. So you construct the parse tree. So the parse tree will be constructed. So we start from S. So S is giving A, then capital A. So this A is been again given as A and capital A, and this A becomes epsilon. So now this one will become B and A, and this A will become epsilon. You travel only the leaf node, you can see A, triple A, then B. So string is accepted. So this is the parse tree for the given regular expression. Okay, now let us discuss about what is ambiguity in a grammar and language. If a context-free grammar is said to be ambiguous, if there exists beta that belongs to the language that has at least two distinct versions of parse tree, then we say the context-free grammar is ambiguous. So ambiguity means a string or word has two or more LMD or RMD trees. So if a string is given, if you are able to derive two different versions of LMD or RMD, then it is called an ambiguity grammar. So even after applying LMD and RMD, the derivation looks different, but the structure of tree will remain same. So you should be cautious that even after LMD and RMD, the tree remains as a same structure. So we cannot jump with the conclusion that the grammar can be ambiguous based on the derivation. So you will decide if a grammar is ambiguous only based on the parse tree. Now, how to check that LMD and RMD with LMD and RMD? So if you are able to get two different parse trees for LMD derivation and RMD derivation, then we can say grammar is ambiguous. Or otherwise, we will try to obtain two different versions of LMD for the same string. Then we can say RMD that a given grammar is a ambiguous one. Or else we can use two different versions of RMD to prove grammar is ambiguous. Sometimes applying LMD and getting a string, then apply LMD to get another string with a different parse tree means that also can be considered as ambiguous. Okay, so the parse tree obtained will be naturally different for each and every string. So now we have to show this grammar is ambiguous. So we have been not given any string, so we will choose the string. So let me choose the string. So the string I am going to use here is, we will take a simple expression ID plus ID star ID. Now how to show this grammar ambiguous is for the given string, if you are able to derive two different parse trees, that is, if you are able to derive two different LMD or unique LMD and RMD means, then this grammar is ambiguous. So let us start with the starting symbol. So here E is my starting symbol, so we will take E plus E. Okay, now I will substitute from leftmost direction, so I will substitute ID plus E. Then this ID plus this E can be substituted as E star E, so I will substitute E star E. Then finally ID plus ID star E, finally this form, and then finally ID plus ID star ID. So I can derive using LMD. This is one method. Okay, so I have derived the string and made that string is accepted by the grammar. So let us draw the diagram for this. So your diagram will be E tends to E plus E. So it's a leftmost derivation, so you will have ID. Then this E is being derived as E star E. Then finally this is ID and this is ID. So we have got a parse tree for the LMD derivation. Now for the same expression, for the same string, can we derive in another format in the same LMD case? Okay, so I will do it in same LMD case. So here I am not going to take E plus E, I am going to take with E star E. So we'll see whether it is able to draw. So I'll start again, it's a left derivation. So from the left side, first non-terminal is taken. So this, it can be replaced with E plus E star E. So this will be ID plus E star E, and this will be ID plus ID star E. Then finally you will have ID plus ID star ID. So for this E and this E and this E, and for this E, this is how, okay, not this one. For this E, we have substituted. Now we'll construct an tree for this. So E tends to E star E. Now this is E plus E. Then we substituted ID from left side, ID. Now you can see the parse tree generated for LMD has two different parse trees. Hence, the corresponding derivation for the given string it produces, I'll write it like for the given string, ID plus ID star ID produces two distinct LMD derivation trees. Hence, G is ambiguous. AMBIGUOUS. So, if you are able to derive two parse trees with the same LMD derivation for the given input string, and if it is both are distinct, then the given problem is the given grammar is an ambiguous grammar. In previous example, we have not given with the string, but here the string is being given as AAB. So now with this rule, so S tends to AS or ASBS or epsilon. So with this, we have to find whether the given string is accepted or not. So first we will do with one method. So S tends to ASBS. Okay. So I will start substituting for this S. So I will substitute AASBS, right? So then I can substitute epsilon for this. So AA epsilon BS. Then this S I can substitute epsilon. So AAB epsilon. So finally it is AAB. So string is accepted. So we'll draw a parse tree for this. So you will have A, S, B, S, and for B I have substituted A, S. Okay. So now for this S we have substituted epsilon, and for this I have substituted epsilon. Now without starting with, I can start with anything. So let me start with, I have to find another LMD if it has a tree. So let me start with AS. So I will substitute multiple AS alone, or to make it comfortable. So what I will do is, I will substitute instead of AS, I will substitute ABS. So because I need B, only term that is having with B is this. So you will have AAS, BS. Then finally for S you can substitute epsilon. So epsilon BS. Then finally you have AAB epsilon. Then finally you will have AAB. Now for this the tree will be is S tends to A, then S. So again S will be AS and BS. Then finally this will be epsilon. So for the two string, when you are using the leftmost submission LMD derivation, we are having two unique parse trees. So we have two LMD parse trees for the same grammar. Hence it is ambiguous. Hence the G is ambiguous. G is ambiguous. So now we have to prove the same way, we have to prove the given grammar is ambiguous. So let us have the same step. So I will take my string as A plus A star B. So in the previous expression it was A plus ID star ID. Here we have two symbols here. So let us see how it is can be generated. So we'll start with the grammar. You can see, so S can be started with S plus S. Okay, so leftmost derivation S can be A plus S, then A plus s can be represented as s star s, then a plus this s can be a star s, then finally we can have a plus a star b. So string is accepted. So you'll draw the parse tree over here. So s will be s plus yes, and you will have a for this, again here s star yes, then finally this is a and this is b. So we instead of s plus s, if we start with s star s, so we'll draw like this. So I'll do with s star s. We can see whether we have a different diagram or not. So leftmost derivation, so you will have s plus s star s. Again this s can be replaced with a plus s star s. So from the derivation itself, it is clear that it is not having same derivation. So you'll be having the grammar ambiguous. So you'll see how it is done. So s star s, so this s plus s, so this is plus, and you have a b. So for the same string, we are having two parse trees for a same LMD transmission. So G is ambiguous. So now you'll see we are given a grammar only with s tends to s, b, s or a. So you have to prove here. Let us find, we will substitute in a different fashion, or you can take an example of any string formation. So you can see here before and after it can be a or multiple combinations. So let us have my string as a, b, a, b, a, b, a. Okay, we'll take in this fashion. So we'll check. So s tends to s, b, s. So leftmost derivation. So we'll have a, b, s again. A, b, you will have s, b, s. Okay, then you will have a, b, a, b, s. So again a, b, a, b, s, b, s. Okay, now I will substitute a, b, a, b, a, b, s. Then finally the s can be substituted as a, b, a, b, a. So this yes, okay, we have substituted this yes, and this yes, and this yes, and finally this yes. So we'll draw the diagram for this. So you will have s tends to s, b, s, only this. So you will have a first, then this will be again s, b, s. So this is again a. Okay, a, b, a, b. So again s, b, s. So this will be a and this will be a. So done. So suppose we can have another possibility. Do we have any other possibility? Can you think about any other possibility? Because if we have some other production, we can replace that production with another production and we can say that this is it. So here the only production we have is SBS. We don't have any other production. So can we form another tree? So I will show you an example. So let us assume SBS. So instead of first s, I substituted a in the previous derivation. Now I will substitute SBS itself. So I am going to substitute SBS, BS. Okay, how many B's we have? 3 B's. Again, for this S, I will substitute again SBS. Okay, then you have BS, BS. Then finally, I will substitute ABSB, SBS. And finally, AB, AB, SBS. Again, I will substitute AB, AB, A, BS. Then finally, you will have AB, AB, ABA. Now we will draw the diagram for this. So you will have S, you have S, B, S. Now this again it is divided into SBS. Again this it is derived into SBS. So now this is A, this is A, this is A, and this is A. So you can see with only one right hand side production with non-terminals, I am able to derive two different parse trees for the same given string. So hence this grammar is also ambiguous. So this is another type of example. So make a note of it. So let us have another example. Is the following grammar is ambiguous or not? So what's the rule we have? So S tends to AS or X and X tends to AX or A. Sorry, this string has to be wrong. So I replace the string. So it's a simple question, but to make you confused, you have given two things. You can see only one non-terminal variable is here, that is a. So it's going to be multiple a generation. So we'll have the tree. So let us have for a, it is going to be ax. Okay. Now for a, instead of s, I can substitute x. Now instead of x, I can substitute ax. Again, I can substitute x. Then final x can be replaced as a. So the parse tree will be is a s. Okay, for this you can have ax, and this you can have another ax. Then finally you can have a. Now the same thing, this is using LMD, we can use RMD also. So I will use RMD to show that they are having difference for the same string. So let us have s tends to, it is ax, so we will take s tends to x alone, then it tends to, okay, we will take the same string, we will take as, then the s will be replaced with ax. So your x can be replaced again with aax, then aax, then you can have a. So now you can see s tends to a, s tends to it is x, okay, as, then s tends to x, okay, sorry, I'll draw it wrongly, yes, then it tends to x. Okay, we have given single x, then that is given to ax, then that is given to, sorry, that is given to a and x, then finally it is given e. So you can see here there is a difference in the parse tree it's created, even though the application is done. So the only difference here is I used two different rules here. So sorry, here also it's ax only, I don't, so it is x, it is yes, then it is given to x. So you can see both is having same parse tree over here, hence this grammar is not ambiguous. So you will be not alone given a grammar is unambiguous. So this grammar is not ambiguous, that means it's unambiguous. So G is, you can tell it is unambiguous. So now the question is obtain the string by applying LMD and the parse tree for the grammar shown below. So it's, so you have to show that whether it can be having two different LMD for the same constraint or not. So we'll have the string, this is the production role, so we have to find two different LMD for the same string. So let us have the first case. I'm going to take this LMD1. Okay, so we'll start with s tends to, we are starting with a. So AB. Now instead of B, I can substitute AA, BB. Now how many A's are there? 3 A's are there. So again I can substitute AB over here, or you can substitute just B alone over here. So we can substitute ABB again here. So you'll have triple A, BB, then you will have one B. Now we have 3 B's, then you have 2 B's here. So we'll substitute that one by one. So B, for this B is substituted, then triple A, B, B, for this again B is substituted. So after BB is substituted, we have A, so we'll substitute A, BB for this. So A, triple A, double B, A, BB. So again I have another A, so the only production with the A is again A, BB. So you will have A, B, B, A, B, B, B. I have 2 B's now. Now I can substitute triple A, BB, AA. I can substitute B, and for this also I can substitute. So I will substitute this one for again B. So you will have triple A, B, B, AA, B, B, then finally. Now I need is BA. Okay. So what I will do is I will substitute BS here. So we'll have triple A, double B, double A, triple B, S. Now for S I can substitute AB. Okay, so you will have so it's double BS. Okay, BB. Somewhere we done a mistake, so we'll correct it over. This is wrong. So BB A again this. So ABB. Okay, BB. So then we'll substitute ABB over here. Then we'll substitute triple A, double B, AB, and okay. So string here is we have to change this. We'll change like this. Okay. So you have B. So then this B can be substituted as triple A, BBA. Again BBS can be substituted. So if instead of S I can substitute triple A, BBA, BB, BA. Okay, and it is capital A. Instead of that I can substitute that as triple A, BBA, triple B, A. So string is accepted. So we'll construct the parse tree for this. So we'll start with S. S is giving A and B. Then this B is giving again A and B and B. Okay, so this B again I am giving it as A, B and B, and for this B I am given B, and this for this I have given B. Now for this B, so we'll take it in this little bit outsider, so I can have like this. So B again I have substituted A, B and B. So for this I have substituted B here, and for this I have substituted BS. Then for this I have substituted B and A, and finally for A I have substituted A. So this is the parse tree which is given for diagram. So we will see another LMD. So the same problem. So we will take S tends to A, B. So the string is we are going to generate is triple A, B, B, A, then triple B, A. So we'll have A, B. So now instead of B, I will substitute again A, B, B. Now for this B again, A, B, B, B. Now instead of this B, instead of substituting B, I will substitute BS. Okay, B. Okay, now instead of this S, I can substitute BA. So triple B, B, capital A, B. Now instead of this A, I can substitute A. So triple A, double B, A, B. So now this B again I need triple B. So I need BB. So what I will do here is I will substitute BS or BB. So I will substitute what has to be substituted. So what's the rule? Okay, A, B, B. So A is substituted as A. So we'll have B. So now B should be substituted. So B can be substituted as BS. So we'll substitute A, B, A. What is that? BA. Okay. So we'll have ABB. So you'll have B over here. So then B, A. Okay, you will have ABB. Okay, again on B and capital B. So this again AABB, BBBS, then finally AAA, BBBA, BBBS capital A, then finally you will have the string. Okay. So we'll see the parse tree how it is constructed. So S tends to A and B. So B tends to A, B. We'll have B a little bit away. So then again instead of this B, so again I have substituted A. B and B. I have three B's. Now instead of this B, I have substituted BS, and instead of this S, I have substituted BA, and instead of this A, I have substituted A. Now for this B, I have substituted B, and for this, I have substituted AS, and instead of this S, I have substituted BA. Okay, and this I have substituted A. So the trees are not identical. So it's A. S can give what S can give? S can give BA only. So BAA. So it's not possible to derive it in the second formula. So we don't have this. So hence it is unambiguous. Yes, unambiguous. Why is it unambiguous? Is we are not able to derive with any other form. Only one form is available. That's why it is unambiguous. So thank you. So that's all about parse tree and ambiguous grammar. We'll see in next section with a new topic.